Started. So just a quick, all right, let's get started. So we're going to have a few quick announcements. This is kind of administrative stuff. So homework one, I guess there was some sort of problem yesterday where half the servers were down. So we're extending the deadline for homework one to tonight, which is Wednesday at 11 p.m. And the hard deadline is going to be still 2 days after that. So that will be on Friday, if you're going to plan to use late days at 11 p.m. OK, homework 2 is out. As of yesterday, this is the sentiment homework for machine learning is out. Another thing is section is going to be, this Friday is going to cover a review of some of the backpropagation and computing gradients, which I went over briefly last lecture, as well as a tour of scikit-learn and some of the features that you might want to maybe use for your project. So come to that. And then next week, Kelvin, who you met during the first day of class, is going to lecture on search, so I won't be here next week. OK, so let's get started with today's lecture, which is the third installment of machine learning. Yeah, so I don't know why this is not working. Did it show up before? Is it warming up? Oh, it's very dim. OK, can I get some help over here? Is it getting better or is it the same?
A little bit.
OK, I don't know why this isn't showing up. Yeah. My mic is also not on. OK. What's?
We're currently working on it. We can hear it inside.
OK. OK. And do you know what's wrong with the screen?
We're also working on that.
OK.
Sorry, a moment, please.
All right. All right, well, while we're waiting, I guess, if you go to cs221.stanford.edu /Q, we can try to talk through this particular poll. So the question is, what is the true objective of machine learning? Is it to minimize error on the training set, minimize training error with some regularization, minimize error on unseen future examples, or to learn about machines? OK. I'll give you a second to think about. And this lecture is going to be some amount of introspection about what we've been doing so far. I think the mic is working now. So we've gone through a lot of the mechanics of how to do machine learning. But this lecture, we're going to explore a little bit about maybe why it works. Why it works is a much deeper issue, but hopefully I'll try to give you an intuition of what is at stake. OK, so we still can't see anything, but you can hear me at least. So I'm going to get a report. OK, so 5 of you said minimize training error. 6 of you said minimize it with regularization. 90 of you said minimize error on future examples. And 5 of you want to learn about machines. OK, so the correct answer here is learn about machines. No, it's about minimizing error on unseen future examples. OK, and this is kind of a really tricky thing, which we'll get to a little bit. OK, I'm just going to continue. So the slides are also posted, so maybe you guys can try to follow along if you can't see. But I'll try to draw more stuff on the board while we have only an audio channel here. So let's just review kind of where we are at the moment. So last time and the time before that, we talked about feature extraction. And the goal here is to take your domain knowledge and distill down into a function that take inputs and convert them into some sort of feature vector. And using that, we can either do, we explored kind of linear predictors. We also explored neural networks. And these are just ways of functions that take a feature vector and transform it into a number called a score. And using that score, you can take, so this gives you a score. And using that score, you can do, we saw binary classification. And we can do regression. Okay, and you can do a number of other things, but so far we've focused on only these two tasks. So how do you compute the parameters of a classifier? We use the loss minimization framework where we define a loss function, and then we use an algorithm like stochastic gradient descent to optimize it. So a key quantity here is the loss. And just to say it again, so these are the parameters of the model, and you want to choose them in a way such that this aggregate quantity is minimized. And this loss function is, remember, if I use a predictor that has parameters w on an input that is x, how unhappy would I be with if I found out the true output was y? Okay, so for classification, we looked at the 0-1 loss, which you can't optimize but you care about, and the hinge loss and the logistic loss. For regression, we had the square loss and the absolute deviation loss. Okay, so a lot of this is kind of like you choosing from you go to a restaurant, you're choosing from the menu. Well, you can pick your classifier, you pick your feature extractor, you pick your loss function that the type of task you want to solve, you pick your loss function, and then you pick your training algorithm. And those are, I think it's important to think about these as distinct choices that you have to make, not that, oh, there's one method that you kind of sign up for, as a package deal. Okay, so are there any questions about the kind of the basics, maybe from last lectures? Okay, so we still have a black screen. It's very, how many, can people actually see this? You can? Would it help if we turn off the lights or something? Would it? Can we try something like dimming the lights? Oh, wow. Okay. All right, so you can't see me, but you can see the screen. No, that was good. Okay, well, whatever. Yeah, let's dim the lights and try not to fall asleep. Okay, so can we dim the lights a bit more?
Someone's coming right now to try and help fix the...
Okay, but in the meantime, can you just maybe make this visible so we can do the lecture? Okay, so it's the other minimize loss, not maximize loss. Okay, so we have this training loss here. And this is a thing that we allegedly say we want to do, right? This is an optimization that we're going to perform. And what question is this actually a good objective or not? And so this is a kind of, this is, if you want to be kind of a pain in the butt, you can kind of give this as a counterexample for why this might not be such a good idea. So here's an algorithm. At training time, you just store all your training examples. Okay? And at test time, your predictor is as follows. So if you're given an input x, if you notice that this input shows up in your training examples verbatim with a particular y, you just return that value. And otherwise, you just segfault. Okay? So this predictor actually minimizes the training error perfectly. But it's clearly bad, right, based on the laughter. So this is kind of ridiculous, which means that this can't be our true objective function. And this is a kind of this is kind of an extreme example of overfitting. So here are some pictures that kind of give you an idea of what overfitting means. I'm not going to go into detail about kind of defining it formally, but suppose you're doing classification and you get a bunch of points which are blue and red, and you want to fit this something like this curve. But there's some noise in your data set. So notice that some of the blue are on this side, some of the red on this side. So if you are trying to get zero training error, you would try to probably fit a decision boundary which is like curves and meanders all the way and tries to classify everything perfectly. And you've just kind of lost the forest for the trees, and this is you're just kind of fitting noise at the boundaries. Another example is in regression, where if you're given a bunch of points that look like this, if you try really hard to get zero training error, getting zero training error is actually even harder in regression because you have to land exactly on the dot. You would probably fit a line that goes through all of these and wiggle through everything. And you might lose the fact that, well, this data is just kind of a line with some noise in it. Okay, so these are kind of the failure modes if you try too hard to fit the training examples or to minimize the training loss more formally. Okay, so then if that's not the right thing to do, then what is? Right? We need a way to evaluate how good a predictor is. And so here the key idea, which most of you kind of already intuitively get, is that our goal is to minimize the error on unseen future examples. And this is kind of natural because what you're going to do in machine learning, you're going to train a classifier, and then you're going to ship it or deploy it in the world, and it's going to get inputs from real users, and it's going to make predictions. Right? Those are things you don't see because unless you can read the future, you can't see that. But you don't have that, right? So that's a kind of the catch because we don't live in the future. So here's the next best thing, which is a test set. Okay, so this distinction here is maybe a little bit kind of subtle and somewhat pedantic, but I think it's important, is that you're gathering a test set which are examples that you just don't use for training. Right, and when I say don't use for training, I mean like don't use for training. And what this test set is supposed to do is it's supposed to represent these unseen future examples. Okay, so now let's just think about the test set instead of thinking about this murky future thing. So when will a learning algorithm generalize? So this is actually a very deep and kind of almost philosophical question because if you think about it, this is crazy, right? So you take this training set and you fit a classifier on it. So yeah, sure, fine, it can fit the training data. But then you go and test it on some completely new examples. You've never seen these things before. Why on earth would you expect this to even work at all, right? So this is, and the answer to this is, one answer is that there is actually some theoretical framework. There's a whole field of statistical learning theory that allows you to answer this question formally. And this is a class 229T that is being taught right now. But we're not going to go into, that's kind of outside the scope of this class. What I'm going to try to give you a sense of is why you might expect this kind of generalization to occur. Okay, so here's a picture which some version of this was presented in the last lecture. Is here's a space of all predictors in the world, and F star is the true kind of the oracle. This is a kind of the function that always outputs the right answer. It's unattainable, but we can kind of conceptually idealize it. And then remember, a feature extraction is by specifying phi, you're implicitly specifying a set of predictors that you're willing to entertain for the purposes of learning. Okay, so let G is going to be intuitively the best predictor in this class in the sense that it's kind of closest to F star. This is the best thing you can do given that you've carved out script F here. And then your learning algorithm, because it only sees a finite amount of data or because it only has finite computational resources, it's going to find some other point, let's call it f hat, in the set. Okay? So now we can understand the gap between f hat and f star in terms of the relationship between G. Right? So there's kind of two parts to this. There's the approximation error, which is the kind of effectively distance between f hat and G, f star and G. And this answers the question, how good is a hypothesis class? How good of a job did you do in kind of feature extraction? And the second part is this estimation error, which is how good is the learn predictor f hat relative to the best possible thing in the hypothesis class, which is G. Question?
How do we quantify the approximation error?
Yeah, so let me quantify it in the next few lines. Question?
Is our family, or is our hypothesis class considered to be given some fixed set of features that we're extracting? Like, can we expand it by changing the features, or is that hypothetically with all the features, this is as well as?
Yeah. So what is f? What is this? Is it basically a fixed set of features, or can you possibly expand the set of features? So for now, we're going to assume that phi is a fixed. So this is a fixed set of features, and we're thinking about this. Of course, you could go and add more features. And this would mean that you would get a larger f, but the same picture would hold for that. OK, so let me try to quantify this. So if you look at the test error between the predictor that you output, the learning algorithm output, and the test error of the true f, this kind of is a measure of how well you could possibly do. Because you can't do better by definition than the thing that always gets the right answer. But you can write this as follows. All I did algebraically is subtract error of G and add error of G. Okay, so you can all agree that this quantity is exactly the same as this quantity. But now it allows me to interpret two terms here. One is the estimation error, which is the difference between the learn predictor and the best possible thing in the class, G. And the approximation error, which is the difference between the best thing in the class, G, and the best thing ever. OK? So all I've done is kind of decompose the error that your predictor obtains into these two quantities, which helps us kind of think about certain trade-offs, which will become apparent. OK. Any questions about this, this picture? All right, so what happens when you, now going back to your question, what happens if you alter the hypothesis class, which means that let's say you increase it by adding more features. You add quadratic features and cubic features and whatever. So your approximation error is going to decrease. Why does it decrease? What? Someone say, why does it decrease? Yeah.
You're getting closer to the real number, to the real classifier.
Yeah, you're getting closer to the real classifier because when you increase this set, this distance is going to be smaller because you're taking a minimum of a larger set, right? So remember, this G is basically the minimum loss over this entire set. If you take a minimum over an even larger set, the minimum can only go down. And the estimation error, on the other hand, increases because, and this is not an obvious answer, because it's harder to estimate something more complex. This is actually, there's a formal answer to this based on statistical learning theory and involves a lot of probability, so outside of the scope of this class. But intuitively, you can think about this as you're trying to estimate a more complex function, so it's going to be harder, and you're going to not be able to do as good of a job. To give kind of say a little bit more about why estimation error becomes harder, I'm just going to give you an analogy. This is a little bit of a loose analogy, but I think hopefully it'll drive some points home. So imagine you're walking by Tressiter and you see a wallet on the ground. Okay, so being a very good citizen, you want to kind of figure out who this wallet belongs to and return it to them. So in the first scenario, suppose that there's just a few people around, and maybe the wallet is you notice that it was just dropped. Well, that doesn't make sense, but suppose for some reason there are only a few people around. So you could basically take the wallet and you can look at its the ID or something, and maybe you only have the first name, and you can go around and ask, is your name Joe? And if you found someone whose name is Joe, then you might be somewhat confident that this wallet probably belongs to them. Yeah. Okay.
One of our labs just failed.
Okay.
We have a center projector that we can bring down. It's bright, but the thing is it covers the boards.
Yeah, I'm going to need the board. So let's just leave this for now, since I think, can everyone see well enough? Yeah? Okay. So, but is this going to get recorded on?
Yeah, your feed is actually getting recorded.
Okay, so the people online are not going to be in the dark. Okay, good. Thank you. Okay, so in the scenario 2, maybe you don't see everyone, so then you go back to your dorm and you email, let's say, all of Stanford, and you ask, is your name Joe? This is a little bit weird of an example, but just bear with me. And then what do you get? Well, a lot of people raise their hands. So now if, for example, you find someone who has, whose name is Joe, it's probably, you're less sure that it's probably their wallet, right? Okay, so what's the analogy here? So here you can think about the people as hypothesis. There's a number of people out there, and you don't know which one of them is kind of the correct or best person to give the wallet to. And you can think about the questions you're asking as examples. So every time you ask a question, you get kind of an example, and that example basically rules out a bunch of hypotheses which are just incompatible. So if the ID says Joe, but someone's name is Alice or something, then it's probably not her wallet. And you can ask more questions like your your last name, for example, and so on. Okay. So the kind of the punchline here is that the difficulty of figuring out the best hypothesis or classifier is kind of really governed by how many hypotheses there are. That's really the kind of the punchline. The more there are, the harder it is going to be to figure out what the correct hypothesis is. Okay, any questions about this? I'm just kind of giving you an intuitive idea of what, how to think about generalization. So hopefully this kind of makes sense. Okay, so let's go on. So now what we're doing is talking about hypothesis size, right? And the idea of, remember that we want to make this small so that, let's see, let me actually just write it out. If you decrease it, then estimation error goes down. But the approximation error will go up. So there's kind of a trade-off here. So let us see how we can kind of manage this trade-off. Okay, so let's go back to linear classifiers or linear predictors. They're specified by a single weight vector W. One thing you can try to do to control the size of a hypothesis is you can reduce the dimensionality, right? So you can think about this this sphere as the set of possible weight vectors. So if you have 3 features, then weight vectors are in 3 dimensions. And you have 2 features, then your weight vectors are in 2 dimensions. And two-dimensional space is smaller than three-dimensional space. I'll just leave it at that. And last time we saw that if you had weight vectors, which let's just work it out. So if you have phi of x equals x, that corresponds to what kind of functions? So you get kind of linear functions that pass through the origin. And if you have phi of x equals x and x squared, then you also have quadratic functions. So there's more functions over here than over here. And this can be seen by the fact that the dimensionality is larger in this case than it is in this case. Okay, so dimensionality is kind of one way to do this. And all this really means is like having more features or less features, if you want. Okay, so here is another way to control the size of a hypothesis. And this is called controlling the norm. So norm is just you can think about norm as synonymous with length of the vector. And this is a little bit, I guess, harder to maybe think about, but suppose we're doing linear regression. So, and phi of x equals x. So your predictor is w dot x, right? Okay, so if you were trying to control the norm, let's say that the norm is less or equal to 1. So for scalars, this is just the absolute value. So w is between -1 and 1. That means, what does that mean for this set of classifier or regressors that you're thinking about? So remember, w is a slope, which means that you're only considering functions which have slope which don't have a magnitude of larger than 1. So you don't have anything like really sharp like this. Okay? So these are the functions. It's between the kind of this range and this range. Okay? So as you increase this, if you increase this to, let's say, 10, then now the slope can be 10, and now you have many more functions. Okay, so just by controlling how the magnitude of your weights, you can affect essentially how many hypotheses you're considering. Okay, so how do you control the dimensionality? You can add features. This will introduce new dimensions. Or you can remove features if they are not helping, if you feel like you have too many features and your hypothesis class is too big. Or there's a kind of automatic ways to do this, which we're not going to mention, but we're not going to go into detail, but I'll just mention quickly forward selection, where you incrementally add features that help drive down the loss the most, boosting, and the lasso or L1 regularization, which allows you to penalize the weights in a way that reduces some feature weights to 0. Okay, so how do you control the norm? So one way to do it is through regularization. So let's write this down here. So for dimensionality, what you can do is basically feature selection. And here, if you want to control the norm, you use regularization. And regularization, all it means is adding a particular term into your objective function. And now you have what is called a regularized objective. And there's different types of regularizers. This particular one here is called a squared or L2 regularizer, which looks at the norm of your weight vector squared, and then lambda is usually a positive number which controls how much you want to regularize, and over 2 is just a convention. Okay, so if lambda is very large, is that more regularization or less regularization? More, right? Because if this is large, that means I want to make W kind of really small. Otherwise, this term is just going to get too big. Okay? And you can think about the other way. It's probably easier if lambda is 0, then this whole term goes away, and there's no regularization, which allows W to be kind of whatever it wants to be, so far as you're minimizing the training loss. Okay, so given this, how do you optimize this objective? Well, you can do gradient descent, which means that instead of just taking the gradient of the loss, training loss, as we were doing before, you differentiate this entire objective, and the derivative of this you can do compute, and that's lambda W. You can check that in it's consistent with the scalar case if you're not comfortable with vectors. And that's basically it. So the intuition here is that you're basically doing the same thing as gradient descent, but you're also trying to shrink the weight vectors towards 0 by some lambda amount. Right? So if lambda is, let's say, 0.1, and your weights are 1, 2, then you're going to subtract 0.1 and 0.2 from your weight vector. Yeah, there's a question back there?
Once the gradient of the training loss gets close to 0, isn't this going to kind of push the weights towards 0 in a direction that doesn't necessarily decrease the training loss?
Yeah, so the question is, if the gradient gets close to 0, so isn't this term going to push your weights in a way that doesn't decrease the training loss? It will do that. So there's going to be some fighting going on, right? So on one hand, this objective this term wants to just send W in directions that minimize the training loss. This one wants to send W towards 0. And often, the 0 point has a high training loss, so this term doesn't want to do that. So there's going to be some negotiation that happens. And when you think about when you're at the optimum, the gradient of the entire thing is 0, which means that the gradient here is always lambda W. So that means the gradient here is minus lambda W. Yeah?
If our training loss is like convex, are we guaranteed that this entire loss together is convex?
Yeah, so if the training loss is convex, this is a convex function, so the sum is a convex function, and you're guaranteed to find the global minimum. Okay, so just a side note, if you use a hinge loss and L2 regularization, that's called training SVM. So I'm putting that there just because in this class we've kind of taken a more general approach to thinking about loss functions and regularizations. And for some choices of loss functions and regularizers, you get things which are standard in the literature. So here's another way you can try to control the norm, which is maybe a little bit more fast and loose. And it's called early stopping. It's you basically take gradient steps, and then you just don't go until convergence. You just stop early. Maybe instead of going for 1,000 iterations, you go for 100 iterations. Okay? So this seems like a kind of a hack, and it is a little bit of a heuristic, but empirically, this has the effect that the weights, if you initialize from 0, are going to stay closer to 0. Because the way they think about it is that at each iteration, you're only moving the weights by some scale that depends on eta. So you're taking a step. And if you stop taking steps after a while, that bounds how much you can kind of move away from the 0 point. Okay, so, and the idea here is, the lesson is you're trying to minimize the training loss because that's what this objective is saying, but you kind of don't try too hard. After like 100 iterations or 10 iterations or whatever, you just call it a day. There's also some theory that shows why this might work, but it's less developed than the standard regularization. So let me just write this down. Early stopping. So in summary, the way to think about all of this is we're trying to minimize the training error, but we're trying to also keep the hypothesis class small, right? And so the idea is just to kind of keep it simple. So just to kind of review what we were doing before, we saw that the error at the end of the day is the sum of the estimation error and the approximation error. And the estimation error, we've argued, is a function of how complex your hypothesis class is, or how big it is. So what we want to do is kind of find somewhat small hypothesis classes that nonetheless fit your training error, so that the sum of these two things is going to be as small as possible. Okay. So, yeah, question.
How does this hypothesis class and reducing its complexity relate to this idea of splitting between a training and a test set? Because in a training set, I could explore a very large set of hypothesis classes, but what does that mean in terms of when I'm studying my optimization or my algorithms on the test set?
Yeah, so how does this hypothesis class relate to training and test set? So we're going to talk more about the splitting of the training and test set in a few slides. So maybe hold on to that thought. So notice that in the presentation of algorithms, there were a lot of what are called hyperparameters. Like, what is a regularization parameter? What is the number of iterations? What is a step size? And these are numbers that do matter in the algorithm, but I haven't really told you a good way of setting them. And that's because there's not really a good way of setting them. But there is a principle which you can use. Okay, so what is this principle? So should you choose the hyperparameters to minimize the training error? How many of you think you should just do that? Okay, I didn't fool anyone. So no, you shouldn't do that, because it would defeat the whole point of regularization. Because in order to minimize the training error, you would say, oh, okay, well, let's just not regularize, lambda equals 0. Or you would try to run it for more iterations. So this isn't super good of an idea. So what about choosing hyperparameters to minimize a test set error? How many of you should do that? So this is not as obviously broken, but I would argue that this is also a bad thing to do, because choosing based on the test set now makes it an unreliable estimate of the error. I think this is a point that's really important to stress. This relates to kind of good machine learning hygiene, is that remember the test set, what is its purpose in life? It's supposed to, yeah. It's supposed to be a representative picture of how well you do on unseen future examples. Now, if you go and you use this test set to optimize your hyperparameters, it's no longer unseen. You looked at it to figure out what the hyperparameters should be. So you shouldn't do this. Okay, so then what should you do? Well, this is where kind of the validation comes in. So you can't use a test set. So what you can do is you can take the training set and you hold out some fraction of it, maybe 10%, maybe 20% of the training set, and use it as in place of a test set to estimate the error. Right? So there's kind of multiple levels of protection. You can think about it that way. So now you train on this fraction, which is the training set minus this held out validation set. And then you can use this validation set to tune your hyperparameters. to set the value of t, the value of lambda, whatever you want. Okay, so and then after that, you have a model, and you're done tweaking. Then you go and you evaluate on the test set to get a kind of final objective measure of how well your classifier or predictor is doing. Okay. So, okay. All right, any questions about this? I think this is actually really important for the practice of machine learning. So I want everyone to kind of understand that, so they don't go and take their test set and train on it or do all sorts of things on it and then say, hey, I got 0% test error. Okay, question?
Is the validation set used in the training still, or is it completely taken out like the test set?
Yeah, good question. So the validation set, is it used in training or is it taken out? So traditionally, it's not used in training in the sense that you don't form the loss function when you sum over examples. That doesn't include examples in the validation set. It's used kind of in an outer loop to tweak parameters. There's also something called cross-validation, which is going to be mentioned briefly in section, which you can split you can have multiple validation sets and average across them, which you can go to section to figure out more details. Okay, so now this is a kind of final slide before we move on to something else. I've talked a lot about kind of the nuts and bolts of how you train and what are the algorithms, but I want to give you a picture of what is it like actually doing machine learning in practice. And some of you might have already some experience, but I just wanted to kind of set a baseline. So I'm going to look at this simple task. It's named entity recognition, a simplified version. We're given a string, like President Barack Obama in, and you're trying to output whether X contains a person or not in the kind of the middle position. So in other words, you're given a word to the left and the word to the right of a particular sequence of a string, and you're asked, well, is this a person or not? Okay. Okay, so here is the recipe for success. And this is just kind of a template to kind of follow when you're doing machine learning. So you have your data set. You want to split it into training, development, and test, where development is, think about it as a validation set. First, you look at the data to get some intuition, the training data, not the test data. And then you kind of enter this loop, repeat. So you try to implement something, you learn a model, and then you kind of look at the training and dev error rates. You look at the weights and to kind of see what is going on, whether it's the algorithm is working or not. You do something called error analysis, which you're going to do in the homework, to brainstorm kind of improvements to the features or your model. And then you kind of repeat this. You implement another model, and then you learn it, and then repeat until you're kind of happy or out of time or whatever. And then finally, you look at, you run it on your test set, and you get the final error rate numbers, and you stick that in your published paper or something. Okay? So let me demonstrate what this kind of looks like on a kind of a concrete example. So this is going to be on this simplified named entity recognition problem. So I'm starting with a training set. So here I have a file where -1 is this entity is not a person. So Mauritius is not a person, it's a country. And this thing is the input. So Sarah Pitkowski is a person, so that's +1. Moscow is not a person, so it's -1, and so on. Okay, so this is a training set, has about 8,000 examples, and we're trying to solve this task. Okay, so here's some boilerplate code which you're going to experience in the sentiment homework, but roughly it basically reads in the training examples, reads in these dev examples, which is a file of the same format. And then you learn a predictor, and you output the weight vector and do some error analysis. And then this part I'm going to comment out because we're not going to try to cheat and look at the test set yet. Okay, so what's missing here is this feature extractor. And that's what I'm going to implement. So this is just going to be a linear classifier on using SGD on top of the feature extractor. And I'm not going to show you submission because that would be the answer to homework 2. Okay, so the feature vector extractor, remember, is a function that takes an input. In this case, x is a string. It's something like this. So x is something that looks like this. And it's supposed to return a feature vector. So let's say it's a phi. And actually, let me make it a default dict of float. Okay, so so far I've implemented the empty feature extractor. So it returns 0 features. Okay, so now let's see how I do. So if I type main.py, this is pretty bad, right? So I basically get error 72%. And that's because what have I done? I've just computed 0 features on it. So it always predicts, I guess, either positive or negative. So let's try to add some features. So let's say phi of, let's see, x equals 1. So what does this do? So remember, I'm using a dictionary representative feature. So for every value of an input, I'm going to have a value which is 1 in this case. Okay, so what do you think this will do? What do you think the training error will be? Should be 0. Why? Because I have a feature for every possible input, and that feature weight can be either positive or negative, depending on whether I want to classify it positive or negative. So when I optimize the algorithm, I can basically, for every training example, either decide, basically fit it exactly. Okay? But if you notice, the test error was horrible because this is a classic case of overfitting. Okay, so let's not do that. So let's do something a little bit smarter. So x, I'm going to split. So this is a bunch of tokens. So this is now a list of all the words. And I'm going to split this further into a left, a right, and an entity. So what this does is the left is going to be the left first word, right is going to be the last word, and entity is going to be the list of tokens in between. Okay, so now I can do something like entity is entity. Okay, so what this does is it creates a feature name, which is this is called an indicator feature, which means that it either is a 0 or a 1. Its value is either 0 or 1. And this simply ignores left and right, and classifies based on this. Okay? I can also define features which are left is left, and right is right. Okay, so what these features do is separately look at the left, which would in this case be took, and the right, which would be into, and try to classify them. So the idea here is that I'm trying to basically distill down this input x into a bunch of little patterns, each of which might be kind of, on its own, might not be able to make a final prediction, but it might contribute a little bit of a signal. Okay, so let's run that. So this seems a little bit more promising. So the training error, I'm not driving it down to 0 anymore because I don't have maybe the full expressive power. But now the test error is actually like somewhat reasonable. It's like 11%. Okay. So now I can look at the I can look at the weights. These weights are generally not, super easy to interpret, but here's a feature that says entity is Clinton, and if it's Clinton, then it's has a positive weight, which means that if the entity is Clinton, it's positive. And then at the bottom, I have so this is interesting. So if left word is the, that means that the entity is probably not a person because you don't say the Percy, for example. Okay, so that's kind of a good sanity check to make sure things are working. Okay, so the error analysis is also interesting. So this shows you for every input in the dev set, so this is the input, what the correct answer was, this was a person, and what we predicted. In this case, we predicted true. Okay, so we can see a bunch of corrects. Here's one that was wrong. So Felix Mantilla, it predicted that it wasn't a person, but in fact it was a person. Okay, and so now you might brainstorm and say, well, Felix Mantilla is like a very specific name. Well, I know that Felix probably in general is a person, so maybe I should define features on individual words. So let's do this. So for word in entity, so for every word in the entity, I can say entity contains word. Okay, so now I've broken down the entity further into features. And I can, let's run it. So now the error rate is 6%. Okay, so now it's generalizing more. And then, let's see, Felix, is this Felix still here? Mantilla, now I get it correct. Okay, cool. Oops, what happened here? My computer froze for a second. But I'm still getting things wrong. And then you can go and, I'm going to stop doing this for a little bit, but you can look at prefix features. So you can, entity contains a prefix. So you can look at the first 4 characters. You can look at the last 4 characters. And, you can check, just kind of, this is kind of more of an art than a science. You just kind of look at, what are the possible phenomena that my model isn't getting, and you can try to brainstorm what are the ways that you can capture this. This is a process, typically known as feature engineering. And now I have a test error of 4%. Okay, so I'm going to stop here, but finally, now I want to go to the test set now and evaluate how well I'm doing on the test set. Okay, so if I haven't screwed anything up, the test number shouldn't be, it should be in the rough vicinity, and roughly it's also 4%. So, which means I haven't overfit in this span of 15 minutes, which is good. Okay, any questions about this flow? So as you're kind of doing your project or your assignment, I think this is something, or machine learning in general, this is, I think, a good way to think about how to make modeling improvements. Question back there.
When we were just initially figuring out which features to put in, the thing that said test error on the right, was that actually dev error? Or was that?
Yeah, good question. So this test error is actually dev error. This is because this function that I'm calling, it just has a hard-coded string test in it, and I'm passing it a dev instead. Yeah. Question?
Can you give an intuitive explanation for why the prefix and the suffix made the classification more accurate?
Yeah, that's a good one. So why did the prefix and suffix help? So one way to think about it is that what are suffix? Let's see. Let me try to see if I can find a real example or not. So sometimes you can do things like maybe if something ends, a suffix would be like something that ends with a Ford, right? So this was Stratford, but you can think of Rutherford or I don't know. There are, I guess, other names that, or like Kazakhstan versus Turkmenistan. There's something in naming it ending in stan might not be might be all kind of related in some way, just like some things that end in forward might be related in some way. So it's just trying to kind of generalize a little bit more. Although this is obviously, there's no hard and fast rules to this. Okay, so I'm going to move on in the interest of time. So, okay, so now we're going to turn to a completely different topic, that of unsupervised learning. I think let's keep the lights. Well, okay, is this good, people? Okay. Okay, so now we're going to talk about unsupervised learning. So far we've talked about supervised learning, where the training data consists of input-output pairs. So this specifies the behavior that we want a particular predictor to have. But in general, as you might find out if you're trying to collect data for your final project, this is very expensive to get fully labeled data. So one of the kind of promising things in, but things which are kind of open challenges in some sense in machine learning is how to do kind of unsupervised learning. And the idea of unsupervised learning is, when you're, just to draw a kind of a human analogy, right? When you're learning things, you don't get like just a huge number of examples of images and you're told the labels of them. What you do is you largely learn in an unsupervised way as you walk around the world and you're processing all the imagery and the sensor in front of you and you try to make sense out of it. And by making sense and uncovering the structure of data, intrinsically, that allows you to get representations which help you for kind of all sorts of other tasks. Okay, so that's a high-level motivation. We're going to focus on, clustering, which is one form of unsupervised learning, where the training data only consists of input points, x. And the nice thing is that unlabeled data is really cheap to obtain. You can think about all the images online that you can download or all the text on the internet. Most of it's unlabeled. And if you can make use of this, then you can really potentially learn a lot. So here's kind of, I'll give you two examples. This is kind of a very classic example of word clustering. Actually, this is the thing that I worked on in my master's thesis and it really got me interested in machine learning and natural language processing. So here's the idea. You take a large set of raw text, and then you run this word clustering algorithm. Details aren't so important. And the algorithm automatically outputs clusters where each cluster has a set of words. So the first cluster contains Friday, Monday, and things that look like kind of days of the week. This has months. This has natural properties and first names of males and so on. So, and what's remarkable is that the algorithm didn't get any supervision about, these are names, or these are body parts or something. It just kind of figured all of this out from raw text. So this is kind of almost a little bit magical, in a way. So here's another example from images. So if you take a huge number of images, which are frames from YouTube, you get pictures of people, faces, which are popular because people like looking at people. You also get pictures of cats because people like looking at cats as well on YouTube. And this is, at the time, really important for getting state-of-the-art object recognition performance. Okay, so the key idea of unsupervised learning is that you have data that's sitting there, and it has a lot of latent structure. So structure that you don't see, and you want to discover the structure automatically. So there's many types. There's clustering, there's dimensionality reduction. In this lecture, I'm going to focus on clustering. So the formal setup in clustering is that you're given n points, x1 through xn, and you want to output some sort of assignment from each point to a cluster. Okay, so here's a picture that you should have in your head. So I'm going to draw points in 2 dimensions for now. So you have a bunch of points. And these points are unlabeled, so they're all just going to be x's. And what you want to do is somehow group these, right? So you can kind of visually almost see here's a cluster, here's a cluster, here's a cluster, here's a cluster. Okay? So somehow you want to group these together automatically. So how do you do this? Well, remember kind of one of our principles is that we kind of want to decouple what is a good clustering from how we come up with one. So first we're going to define an objective function that captures clustering, and then we're going to try to figure out how to optimize that objective function. Okay, so this is called k-means, and I want to distinguish between k-means, the objective function, and k-means, the algorithm, which some of you might be familiar with. So the objective function is going to be based on, so let me redraw this so it's easier to explain. So let's say you only have 2 clusters, so k equals 2, k is the number of clusters. What I'm going to think about is like, why is this a cluster? Well, the points are kind of close together. In a particular, k-means says, I can figure out a centroid, a particular prototypical point, such that these points are all close to that centroid. And over here, why is this a cluster? It's because all of these points are close to that's not actually the centroid of these 4 points, but whatever. All of these points are close to the centroid. So what I really have here is I have centroids, mu, and this is going to be mu1 through mu k. So in this case, it's mu1, mu k. And I'm also going to have assignments z, and this is going to be z1 through zn. Remember, n is the total number of points. It's 8 in this example. Right, so these are the variables of the optimization problem. I want to find both centroids. Where do I place these kind of prototypical points such that I can assign each of the data points to one particular centroid? So z1, let's say this is x1. z1 is going to be assigned to 1 and so on. Okay? So for any setting of centroids and assignments, I'm going to have a particular I want to define some particular number that captures how good that clustering is. Okay, so this is kind of what I've said, and this is the objective function. So what this says is this is the loss function, which now depends on the assignments z and the centroids mu. And this is a summation over all the points. So for every point xi, I'm going to look at the distance between that point and mu of zi. So remember, zi is an index that specifies which cluster I'm assigned to. And mu of zi is the centroid of that cluster. Okay? So this distance is basically going to be the length of each of those blue edges. So think about taking all of those blue edges, taking their length, squaring them, adding them all up, and that's the number that is the objective function for k-means, also known as the reconstruction error. Okay, so let's do a kind of a simple example just to illustrate kind of the ideas here. So doing things in 2 dimensions is going to be somewhat more annoying. So I'm going to look at a single one-dimensional example. Is it better if I write over here? Is it brighter or? Okay, so let me try to do that. Let's see. Okay. So let's do it over here. Okay, so here's a one-dimensional example. So you have 4 points. This marker's running out. Let me use another one. So there's going to be a point at, let me use green, at 0, a point at 2, a point at 10, and a point at 12. Okay? So there's 4 points. And I want to cluster them, let's say, into 2 clusters. And visually, you can kind of see, well, these should be in one cluster and these should be one cluster. But how do we do this algorithmically? So here is kind of an interesting observation. So let's simplify the problem. Suppose I told you the centroids, 11 and 1. Okay? So if I have the centroids at 11 and 1 respectively, so this is 1, this is 11, and I asked you, how do I assign points to centroids? How do you do that? In the best way possible.
Wherever the difference is smallest.
Yeah, you look at this, where the difference is smallest. You look at this one, well, that's a difference of 1. You look at this one, that's a difference of 11, which is smaller, 11 and 1. So I'm going to basically assign this point to this cluster, same here, and same here. Okay? So this is what these equations are showing, is that for each of the 4 points, I can just compute the square distances, or equivalently the distances, and just choose whichever one centroid is closest. Okay? So easy, right? All right, so what about in the other direction? So suppose I told you what the assignments were. Suppose I told you that basically all the blue edges are known. So I know that 0 and 2 are in the same cluster, 1, but I don't know where the centroid should be. So where should I put the centroid? Well, you look at the objective function, and you look at the, well, let's see. Well, okay, let me just kind of explain this intuitively. So you look at all the points which are assigned that into the cluster 1, and you simply average them. Okay? Because a centroid is the center of gravity of all the points inside a cluster. So if you know that all these points should be in one cluster, you just average all their values, and you get 1 in this case and 11 for the second one. Okay? So now the problem is that I don't even know mu, and I also don't know z. So it's a kind of a chicken-egg problem, where if I knew one, I could get the other, and if I knew the other, I could get the one. But how do I begin? So here is a key idea, which we're going to see later in the course as well. It's called alternating minimization. And we're going to take this hard problem and try to solve it, tackle it by solving 2 easy problems. So here is that, and that gives rise to what is called the k-means algorithm. So k-means algorithm has 2 steps. Step 1 is you're given the centroids, mu1 through mu k. So those are the red squares. And then you're going to try to assign each point to the best centroid. Okay, so mathematically, this looks like this. But intuitively, you just, for each point, you just look at each centroid and compute the distance, and you take the centroid that is the closest. Okay, and then step 2, you're going to flip it around and say, hey, there's some cluster assignments. I'm going to find the best centroids. You're going to go through each cluster. You're going to set the centroid to the average of the points assigned to that cluster. So in formula, what this looks like is that you look at all the points and add them up and divide by the number of points assigned to cluster K. Okay, so the whole algorithm is you initialize the centroids, you set the assignments given the centroids, and then you set the centroids given the assignments, and you keep on iterating. Okay, that's it. So let me show you a quick demo of what this looks like. So can people see this? So here I'm creating a bunch of training examples. And then, okay, so I initialize the centroids here. Okay, so there's 3, k equals 3 here, so 3 centroids. And then now I'm going to assign points to clusters. Okay, so now I assign these points to this cluster, this point to this cluster, and so on. And now I'm going to re-estimate the centers. So boom, those basically, this point gets set to this average of these points, and so on. And then I'm going to reassign the points, and then estimate the centers, estimate the cluster assignments, estimate the centers, and so on. So you can see that this is an iterative algorithm that eventually kind of converges and has a loss of 44.17 in this case. Okay. So any questions about how k-means work, either intuitively or mathematically? Yeah.
So you choose the number k, but how many clusters?
So the question is how do you choose k? So so if you choose it too small, then you're going to have really high training error, and it's not going to fit your data very well. If you choose it too large, like if you choose k equals n, then you're going to get 0 error, and you're going to overfit. So it's kind of the same story as before. You choose it by either validation, or you can look at the training error as a function of k. So as you increase k, it's usually going to come down, and if it looks like you're getting kind of no gains after a while, then you just truncate at some point. Yeah, question?
Does your initial centroids, like selection of centroids, have a big impact on?
Yeah, so that's a good point. I'll come back to that very question. Okay, so in a few slides. So let's do this on a simple example here. I guess we kind of did this already, but do people want me to go over this example? How many of you want me to step through this 1D example again? Okay, not that many. So maybe I'll skip this. I'll just go over it briefly. So if you initialize with instead of 1 and 11 on the board there, you initialize at 0 and 2. Right, so those are definitely not where the centroid should be. In the first step, you're going to assign the first point to the first centroid and everything else to the second centroid, which is also not right, but you're going to re-estimate the centers and they become 0 and 8. And then in the second iteration, now you're going to get the assignments right, which is going to allow you to estimate the means. Okay, so I recommend you kind of working out this example by yourself if that doesn't make sense. Okay, so now let me get to the question here. So the question was, does the initialization matter? And the answer is yes. So it can be proven that k-means is guaranteed to converge to a local minimum, but it's not guaranteed to find the global minimum. So as we saw in this one example, k-means did converge. In that case, I think it was a global minimum, but if you choose, I'm going to change the random seed here. So if you initialize in a slightly different way, suppose you initialize like this, you run k-means, you end up in this situation, which has a loss value of 114 instead of 44, and it's clearly a lot worse than the other solution. And you can play around with this. Well, what happens if I try a seed of size 10? Then this gets something which is also not right, but it's close. So 11. So this one happens to get the right thing, and so on. So you can kind of play with this. This demo is online, so you can check it out. But so typically what people do is you run multiple times from different random initializations. And you can also initialize more cleverly using this heuristic called k-means++, which tries to put the centers far away apart so that they kind of don't interfere with each other. Okay, so that was kind of a brief overview of unsupervised learning. We looked at one particular example, which is k-means. And in general, I should stress that this unsupervised learning, typically the problem is much harder, both kind of conceptually but also computationally. And what we showed here is a simple alternating minimization algorithm for optimizing the k-means objective function, which surprisingly actually works pretty well in practice, even though it's not guaranteed to find the global optimum. Okay, so let me step back a little bit. This is kind of concluding the section on machine learning. So there's a few concepts which are important to go over. So first, feature extraction, defining your phi. That defines this hypothesis class, which, remember, controls the set of possible candidates you're thinking about. Larger hypothesis class tends to overfit more. Smaller ones tend to underfit, and so on. So it's kind of art to get this right. You can use a feature to do prediction, either using linear models or neural networks. You can set up loss functions and optimize them using gradients, which we saw kind of two ways of optimizing. Stochastic gradient descent for the supervised learning case, and alternating minimization for k-means, but you can actually use different, these are just 2 points in the grand space of things. And then I think there is this kind of maybe appreciated fact about the practice of machine learning, that there's this kind of development cycle of trying to improve your model by looking at your data, which I think only comes with practice. Some kind of historical notes. So the idea of machine learning actually goes way back, to maybe you can trace it back to Gauss, who used least squares. He was the first to use least squares to basically fit a model to the positions of celestial objects. Logistic regression, which is related for binary classification and was studied in the 40s in statistics. In the AI community, in the 50s, Arthur Samuel actually built a program to play checkers, which was actually based on learning. So people invented the perceptron algorithm in the 50s. And then actually what interesting happened is that in the end of the 60s, Minsky and Papert wrote a manuscript that essentially showed that the limitations of these kind of linear classifiers. And that actually kind of caused research to kind of stall on that. And then AI became much more kind of rule-based and symbolic. So it's interesting that a lot of these ideas were actually around much earlier. And then we know that recently there's been kind of a revival of neural networks and other ideas. Okay, so just kind of going forward, there's a bunch of interesting challenges. As I mentioned before, unsupervised learning is still very hard, and you can think about prediction problems like producing an image or a translation, which are much more complicated than the ones we've looked at, but in some sense they're based on the same principle, like the idea of loss functions and scores and SGD. They're actually really kind of the same thing. So make sure you understand the basics. There's also a bunch of concerns that one needs to pay attention to. So when you deploy machine learning, actually the predictions affect user behavior, which is actually used to generate data. So there's feedback loops which are not really well understood. There's been a lot of recent interest in finding classifiers that don't discriminate against minority groups and so on. There's the issue of privacy. Do you want to upload all your data to the cloud? Can you actually privatize? So if I want to protect my privacy, can I upload some information to the cloud, and that allows, let's say, some big company to train a classifier that still works well and still not reveal my identity? So that's really interesting. And then there's a topic of interpretability, especially with things like neural networks. How do we understand and what they're doing? So I should kind of, when you take, the main takeaway I think at this point is, learning is something that we're not done with yet. It's this general idea that systems should kind of improve with experience. And we're going to see learning throughout the quarter. So next week, we're going to look at state-based models, which are going to be more powerful than the kind of these reflex-based models that we've seen so far this week. OK, that's it.